All right, guys, so yesterday, just to recap, we looked at this worked example 17 stuff, all right, where we spoke about the types of x-intercepts that you can get, and this table, or not table, sorry, this like block at the bottom, where we said that if you have a factor with an even exponent, then it will be a turning point, all right, on the axis. So there, for example, and over there. And if the factor, whether it's just an x or a bracket, if it has an odd exponent, then it will cross through the x-axis at that point. Okay, so that's where we left off yesterday. Now, this is just basically a summary of the different shapes, I suppose. And the ones here at the bottom look very complicated, but what we're actually just looking at is what happens to the left and to the right. Okay, so what they said here is that if you have a polynomial, so you can just highlight that. Yeah, so they do actually say right there at the top, they're saying to determine what happens to the graph as x tends to infinity, okay, so to the right, or as x tends to negative infinity. So that's actually what this table is summarizing, okay. In between those two parts, you can have all sorts of turning points, x-intercepts, and so on, but this table is just talking about what happens to the left and to the right. Okay, you'll see here in the kind of summary. So here, the important stuff is an, which we call the leading coefficient, all right? In most cases, we would call that a. So if you have a parabola, for example, it's ax squared plus bx plus c, all right? The leading diagonal is a. So the leading diagonal is, sorry, not diagonal. I'm thinking of matrices here. The leading coefficient is the coefficient of the variable with the highest exponent. Okay, so if it's a parabola, okay, if it's a quadratic equation or quadratic function, the degree is 2, it's an x squared. So the number in front of the x squared, that is what we call the leading coefficient. Okay, and we all know that that is also what tells us the shape of the graph. So if we have n is now the degree. So that's the other thing that's important here. Maybe we can just write somewhere there. When they're talking about n being even and n being odd, that's the actual degree of the function. All right. So the highest exponent of x would be n. And then here on the side, they're saying if your leading coefficient is positive and if your leading coefficient is negative. Okay, so they're summarizing what happens in terms of the sign of your leading coefficient and whether the degree is even or odd. Maybe I'm just going to write leading coefficient there at the top. Okay, now guys, if we're looking at, yeah, for some reason they have like the basic parabola and the basic cubic graph, I think just because that's what we're familiar with, and then they generalize it to any higher degree of either 2 or 3. So here, if n is even, right, do we have an x squared, the basic parabola, y equals x squared. If your leading coefficient is positive, if a is positive, we all know that we have an upwards facing parabola, right? Is that fine? Okay, if we're looking at the cubic graph, now n is odd because for a cubic graph, your degree is 3. All right, so your degree, your n value would be 3. Now, if your a value is positive for a cubic graph, it is an increasing one. All right, it starts by going up. And then to the right, it will also rise. So this is what they're saying. They're saying falls to the left, falls, I suppose, and rises to the right. We haven't really used that terminology before, but does that make sense? Right? So on the left-hand side, it's almost like it's falling. The y values look like as you're tending towards negative infinity, they're getting smaller. All right. So as you're going to the left, the y values are getting smaller. That's what they say. And as you are moving, as you're tending to positive infinity, as you're moving to the right, the y values would be getting bigger. Okay, now this is what's going to happen if you have any higher even degree, okay, or something like this. There could be, here we have a turning point in between negative infinity and positive infinity. I think we actually drew a graph that looks like this. Can you just quickly go back in your books for me? I'm pretty sure. What was that equation, Krista? Do you have it there? No? Okay, it's fine. Fine. Okay, so it was an x to the 4 equation, essentially, if we were to multiply it out. Okay, then we got this kind of situation. So guys, it's nice if we're remembering the basic parabola, okay, because that has an even degree, right? And if your a value is positive, it's like an upwards facing one. So now if you have an x to the 4, an x to the 6, or an x to the 8, don't worry, I've never drawn an x to the 8 one, I'm sure you won't have to. But if you have any higher even degree and your a value, your leading coefficient is positive, it will still have that kind of shape where it's going to rise to the left and rise to the right, but in between other stuff might be happening. Okay, in this case, this example that they've drawn here, we would have a turning point in between. Okay, so that just kind of helps with the shape. Obviously, you would have to find points and x-intercepts and turning points and all sorts of things. Okay, but if you're confused about the shape, because often that happens, right? We have a graph and we have a bunch of points and we don't actually know how we should connect them. Okay, then that's what it would look like. Then the other thing is true that if your leading coefficient is negative, we have a downwards facing parabola, all right? If it's an even exponent there, an even degree. But then for any higher even degree, it will also be like a downwards facing parabola, but there will be other stuff happening in between. Okay, does that make sense? This column here. It's nice if we think of the parabola and then we can just kind of adjust what happens in between. Okay, if we have a higher even degree. Yeah. It won't be a lot. Like, let me just see the ones that you're going to draw today.
But like
it's not that bad.
Like the higher the degree gets.
Yes, the more things you will have happening. Yeah.
So it could be like,
in theory, yes, but in practice, don't worry about that. Okay, let me just see here because I have drawn a couple of the ones in the textbook, and I think the highest one that you have to do is x to the 5. You're going to do an x to the 5 one today. Okay, this is not that. I mean, it's not, yeah, it's worse than this, but it's not that bad. Okay, then for the cubic graph, all right, if your leading coefficient is positive, you fall to the left and rise to the right. Okay, if you have an even degree, sorry, odd, sorry, my bad, because it's cubic, odd. But now if you have any higher odd degree and your leading coefficient is still positive, it will have that same shape as you're tending to negative infinity and to positive infinity, all right? So it will still fall to the left and rise to the right, but you can have other turning points and things in between. Okay, similarly, if you have a negative leading coefficient, we're thinking of the basic cubic graph. So now we're looking at an odd degree, okay? Because for a cubic graph, our degree is 3, which is odd. It's this kind of shape. It's a decreasing graph, all right? So to the left, it rises, and to the right, it falls. Okay, same thing if you have a higher odd degree, then to the left, it will still rise, and it will still fall to the right, but you can have other stuff happening in between. Okay, that's just in terms of the shape. In terms of understanding, now that you've plotted all your points, where is this thing supposed to go to? All right. Now, guys, in AP, they're not as finicky as in core in terms of how many points you need to plot. So I know that when we draw, and it will come up when we're going to rational functions specifically, but if we're drawing a hyperbola, for example, you have to have 2 points here and 2 points here, right? In AP, that's not the case. You just calculate the points of interest, they call them, all right? The important points, your y-intercept, your x-intercept, your turning points. If they ask for it, same as in core, you're going to calculate your point of inflection. But remember, sometimes your turning point will be your point of inflection, all right? Like we discussed yesterday as well. And then you plot them, and then if you can just figure out the shape in the parts that you don't actually have points, you don't have to plot more than those. All right. So it is sometimes quite useful also if you don't know what your graph should look like. If you don't know what should happen over here, you can sub in an x value, and then that will show you obviously where your graph is going. All right, but it won't be the case of like if you're drawing a hyperbola, you have to have 2 points here and 2 points here. Okay, it's more you plot the intercepts, the turning points, whatever, and then the shape must just be correct from them. All right. Okay, guys, I'm going to give you 3 graphs to draw on your own. You're going to do this at the normal thing. You're going to find your y-intercept, find your x-intercept, find your turning point, plot them, all right? Connect them. And then this table could help you to figure out the shape. If your points don't give you enough information to actually draw the shape properly. Okay, so refer back to this table. I'm not going to do an example because it's going to take quite long and I rather want you guys to try some on your own. But there are examples in the textbook, I'm sure, if you want to look at that. But just try on your own first. Okay, you can actually get marks just by plotting the normal points like the intercept and the turning points and so on. Page 199. I want you to do number 1. Now, guys, in number 1, they say that you don't have to find the coordinates of the turning point, which makes it quite difficult if you don't have the coordinates. So I would suggest that you do actually find the coordinates of the turning points. Okay, do it properly. The coordinates just aren't very nice. They're like decimal coordinates and so on. But another thing, guys, remember in AP, if you have a quadratic or cubic equation, whatever that you're trying to solve, just use your calculator. Okay, if you have your equation equal to 0, type it into the calculator and solve from there. That will also save you a lot of time. Okay, so these are 3 graphs, I think. It's 1A to C. That's what I did. Can someone just check if that is actually, anyone have a book here? A to C. Okay, thank you. And guys, there are more, all right? So when we mark these graphs, if you feel like you need more practice, you can do the others as well. And I think you all still have your solution book, so you can then mark from there. I'm not going to take them back in and hand them out again, all right? You are going to keep them now until the end of the year. But yeah, I urge you to actually still do the homework and not just think you have the solution, so you're just going to look in the book. Okay, you do need some practice on your own. So get going on those, please. 1, A, B, and C. And that is then for, we'll mark those on Thursday. Okay, so we're going to do 4 tomorrow and on Friday.